I am Sandor Lehoczky. I am the project scientist for the Material Science Research Rack on the station. And this presentation was supposed to be given by Dr. Frank Safran, but he couldn't come. So I hope I can make a faithful presentation of his charts. I kind of was really was hesitant to come up here after all these nice presentations that I am especially pleased that I didn't have to come up after Neil. I would like to point out that material science is an applied science, and as Bob Bloodis pointed out, who used to be heading the Bell Labs for a while, everything is made of something. Let me have the next slide. Well, already I think it has been discussed rather extensively. Space provides lots of unique aspects for research. Heat and mass transfer in most cases predominated by diffusion, near absence of gravity-driven convection, restricted hydrodynamic shear, no sedimentation, and so on. Now, one thing I would like to point out, the question of let's take it off, then I can move around. Would like to point out the question of orientation of the residual acceleration came up. Indeed, even at 1 micro G, the orientation is very important. In fact, in one of the Space Lab missions, I had an experiment where I was growing a crystal at 4 millimeter a day, and there was a change in the residual acceleration direction by 0.3 micro G, and I looked at the compositional variation in a crystal, and that picked it up. Matter of fact, everybody said there it didn't happen, and later on we went back to the acceleration measurement system, and sure enough, the space shuttle was passing. So indeed, residual acceleration is important. And the important thing in solidification is the solidification velocity vis-a-vis the flow velocity. So for example, if you grow crystals, protein crystals or whatever, if the growth velocity is 1 millimeter a day, then and flow velocities of that order will have a significant effect. May I have the next slide? Well, the question comes, why do we material science in reduced gravity? In most materials, you have multi-component systems. In semiconductors, you have dopants, impurities, and in metals and alloys, you have various metallic components. During melting and solidification, because of the temperature effects and composition effects, you can have large density gradients which drive convection. And consequently, whenever you solidify something, you will have a variation in the distribution of that components. It's very critical, especially in semiconducting materials, where the electrical and optical properties extremely depend on component distribution. Like in any activity in a lab, the control of the various parameters is very important. In low Earth orbit, you have an additional control parameter, and that is gravity. Now it came up that in Earth, you can simulate variations with gravity by using centrifuges. And I was listening to it, I thought about it. It's good for stationary systems, but if you would have an animal or something moving around, there is an additional force, the Coriolis force comes in. So it really complicates the interpretation of the effect like you would see in a centrifuge. Well, in material science, you can do lots of scientifically interesting things. And for example, grow benchmark materials which give you and you can determine the ultimate material performance limit. Measurement of very thermophysical properties. We're doing lots of theoretical modeling of the solidification process, and especially with the tremendous amount of growth in computational capabilities. Well, any computation is as good as the boundary condition or the thermophysical properties you put in. And so measurement of having accurate thermophysical properties is very important. The bottom line for this activity, since like I pointed out that material science is applied science, the bottom line is we're doing these experiments to come up with improvements in material processing on Earth. May I? Next one. Like I pointed out, I am the project scientist for the material science research track on the station. And this is the facility. This is a joint activity between the European Space Agency and Marshall Space Flight Center. The facility is it's a modular facility, and it accommodates various furnaces, and the furnaces have been provided by the European Space Agency. If you switch to the next slide, I give a schematic presentation of the facility, and it shows you the modular nature. Here you see the process chamber, the sample cartridge assemblies, and the furnaces. And you see that once right now we have the facility on orbit, and you only have to carry up the sample cartridge. So it's really, really improved the efficiency how we can do experiments on the station. When we were doing experiments on Skylab, you still can hear me? When we were doing experiments on the Skylab, we usually had to fly the whole system. And you flew an experiment, and you might have done other one within another year or two. Here we can do lots of repetitive experiments. So this is a really increases our capacity to do interactive research. May I have the next slide? I was telling you that it's modular facility. This, as you can see, this is the cartridge. It shows you the sample, and since the furnace operates up to 1400 degrees centigrade, safety is really fire safety very important. So you see that this cartridge provides for the various safety addresses the various safety issues, and also you can take up various samples. May I have the next slide? And I would like in the next few slides just run through some of the experiments we have been recently brought back into the program. And these experiments are done in collaboration with some of the ESA investigations. And the first one here is really addresses the question of the development of microstructure in alloys during directional solidification. The precise control of the microstructure is very important because it has a large effect on the mechanical properties of the material. The other set of experiment looks at the pattern formation, especially in casting. Casting is a very large industry, and controlling the various casting parameters is a very big issue in a metal processing industry. May I have the next slide? Then we have other experiment, which is involves the crystal growth of cadmium telluride and related compound semiconductors. And why we're doing those experiments are those are very important materials for radiation detections, X-ray telescopes, matter of fact, detecting of nuclear materials. And you really need a high resolution to pick up various separate isotopes. And these materials are a materials choice by the Department of Homeland Security for looking at try to detect materials and at the entry port in the United States. And this just shows a couple of examples on the crystals you grow on Earth. And in the Earth experiment demonstrated that the styrations you see there are really, and steps are really dependent on the relation to the gravity vector. May I have the next slide, please? This experiment is looking at the effect of contact between the container walls with the solidifying crystals, in this case, in germanium silicon alloys. And to illustrate the effect of contact with the container wall, you see where the containers contact the walls, there is a large number of so-called dislocations, which are defects and which are very important in electronic materials because they serve as electron hole recombination centers and greatly affect the electrical properties of the material. And you see where the material was attached to the wall, there is a large number of that defect. And when it was detached, like here, and you see a great amount of reduction of the defects. That's one of the experiments, is looking at the detached solidification, as you see in the bottom of the figures. The other one is the so-called melt zone, melt growth. one of the nice things in space, that zone can be extended to the Rayleigh limit without having to, so you can, that really affects your, how you have, can transfer heat and mass transfer on the during crystal growth. So I am not going to go down through, you can read it, the various, why we doing it and what the relevance of this is. This is again a joint experiment which we're doing with the University of Freiburg. Next slide. There is also a facility developed by the French Space Agency, and I don't try to read the name of it. I just call it DECLIC. In fact, I had a weekly note sent up to the director of engineering, and it came back and they asked me what DECLIC stood for. And I took me a while to try to find a translation for it. But this facility is really more like a fluids facility, but we're doing some materials experiment in it on a transparent module system. May I have the next slide? Here, Rohit Trivedi from Iowa State is using Sucillo-neutral model to look at the solidification. And this is a really nice demonstration what happens depending on the growth velocity, what happens front of the solidification front. If you go really slow, you have a plane front. If you increase the speed, you become so dendritic, and the nature, matter of fact, most metals you use are solidified by dendritic solidification. And the shape and the pacing of those dendrite trips is really depends on the growth velocity. But on the other hand, it's really affected by fluid motion. Matter of fact, the fluids can break up some of those dendrites and really changes the nature of the microstructure. Also, those dendrite arms really can be affected by the fluid motion. So the reduction of gravity and elimination of fluid motion have a very significant effect on the shape and form of those dendrites. And so we are essentially generating here a unique data set in microgravity, which we can use to test the validity of the various dendritic solidifications proposed. And this is a very nice experiment, and it is being done in this facility on a station, which have been built by the French Space Agency, and it is integrated into the Express Rack, which was developed by Marshall Space Flight Center. May I have the next slide? Other very nice experiment, and this is managed out of the Glenn Research Center, is the coarsening of solid liquid mixtures. And this is, I think, a lead tin system, and it looks the coarsening of particulate matter embedded in a fluid. And you saw some reference to it earlier. And but let me show you the actual, may I have the next slide? experiment here. You see on a ground, if you try to do the experiment, the solid particulate matter migrates to the top. On the space, you get a very nice distribution of the solid embedded in a melt. And the part of the experiment is to get a really nice distribution. Then you look at it with time, as with diffusion, those particles start to grow expense of each other. So there is ripening of the solid phase. Next one. Also, we have two experiments, and hopefully try to manifest some more to do some containerless solidification and thermophysical property measurements. And what we're using is the electromagnetic levitator, which was developed by the German Space Agency and ESA. And you can actually levitate metallic particles on the ground by using RF fields, radio frequency radiation, just from the Lorentz force applied. But you have to have really strong fields. In space, we also having some forces applied, but you really have much lower forces and can really undercool materials if you levitate them, because lots of the solidification and nucleation is induced by the container wall effects. Matter of fact, for example, in tungsten, can be undercooled below their melting point by 400-500 centigrade if it doesn't have contact with a container. And what is interesting about it is you can get phases in the material which you wouldn't get under normal solidification. So you can get materials with very unique properties. Matter of fact, you can get some glassy metals experiments, and this is the the available there, but well, it has been a fire wall has came up. So except for a government, it's hard to access. So we're thinking about how to get this out to the public. But there is also some information in this space science resource study that NASA report. And if I can provide further information, don't hesitate to call me. But as I pointed out, Frank Safran is the responsible for the material science program. We used to have a very extensive program, but it has been really cut back a lot. So we're trying to build it back up. So matter of fact, we had a AO recently out, and we will be selecting 6 more experiments, hopefully this month. Thank you for your attention. And if I can answer any of your questions, let me know.
I was wondering if anyone has modeled fusion welding and solidification process in microgravity.
Welding?
Fusion welding.
Fusion.
Yes. And
Matter of fact, that would be really good to do. And actually, as you brought it up, you notice the rack I had up there? The left side of it was empty. And it would be nice to actually put up some experiments using fusion welding. Now, we didn't do fusion welding, but we did some interdiffusion studies, and where you took two liquids, put them in contact, then looked at the interdiffusion, froze the sample, then bring it back and slice it. But yeah, it would be very good to do fusion welding studies and soldering, yes. Because if we go on long missions,
that will be having a lot.
There has to be some provision for repair, right, and fixing things.
Right.
Because you cannot carry that many replacement, yes, parts.
Thank you.
Any more? Thank you again.